Hi everyone, and welcome to today's video on matrices. Matrices are one of the easier topics in A-level further maths. It isn't revisited in year 13, and what you do have to know is quite formulaic, even though of course aspects like inverting theoretically matrices have a reputation of being pretty painstaking. I've tried to cover all the main concepts in chapter 6 today, but especially focusing on matrix systems of equations, because it's probably the hardest part, especially the geometric configurations. I personally find the textbook rather unhelpful for that aspect, and you may or may not have properly understood it depending on the quality of your further maths teacher, so I'll try to be really clear about how I deal with those. Moving on to the top tips, first one is to memorise the rule for multiplicative conformability, and that just means whether matrices can be multiplied together. So in order for that to be the case, the columns in the first matrix have to equal the rows in the second matrix, the number of rows in the second. And of course, based on that tells us that matrix multiplication isn't commutative. The order that you do it in matters. So yeah, C comes before R might just be a good way of remembering that. Practice multiplying matrices of different sizes to get familiar, not just multiplying square matrices. That can be something that helps. Practice inverting 3x3 matrices by hand. Usually you can use your calculator, but if they put in an algebraic term like an A or a K, then you have to do it by hand, so you have to know that, unfortunately. And to learn the geometrical differences in linear equation sets. For example, if a set system of equations is consistent, the planes might form... that should say inconsistent. If they're inconsistent, then the planes could form a prism or be parallel. Moving on to the questions. So first one, we're multiplying together two matrices which are different sizes. So AB is going to be that, essentially. Excuse the fact that I couldn't put brackets around it when I was making the question sheet. Anyway, to do this, we're going to look at multiply the elements in the row on the left-hand matrix by the elements in the column on the right-hand matrix. That's very difficult to say. So we have 1 times 0, add 3 times 1 for our first element. Second element is going to be 1 times 1, going from here to here. 1 times 1, add 3 times 3, and then we have 1 times 4, add 3 times 5. On the bottom we have 2 times 0, add 4 times 1. We have 2 times 1, add 4 times 3, and we have 2 times 4, add 4 times 5. Which, if you compute those, gives you 3, 10, 19, 4, 14, 28. And we also had to explain why BA does not exist, and it's because of the rule we said earlier. In order for two matrices to be multiplicatively conformable, the number of columns in the first has to equal the number of rows in the second. And if we did it with B first, then multiplied by A, the number of columns in the first would be 3, and the number of rows in the second would only be 2, and therefore that's why you can't multiply them together. Next one, we've been given a 3x3 matrix, which contains an algebraic variable in it, A. And we've been told where A is a real constant, state the values or value of A for which M does not have an inverse, and then find the inverse in terms of A, given that M is non-singular. So non-singular means that the determinant is not 0, and M will not have an inverse if det M equals 0. And that's because when we're inverting a 3x3 matrix, one of the parts of that inverse is going to contain 1 over the determinant. Of course, you can't divide by 0, so that's why that won't work. So to find the determinant of the matrix, we will use minus. So the way I like to think about it is if we're looking at the minor of 3, cover up the row and cover up the column containing 3, and the remaining, I guess, 2 by 2 matrix is what we're going to write down. So we have 3a minus 1, 1, 1, minus 4, 1, add 5, 1a minus 2, 1. If you put that together, we get 3a plus 1 minus 4, 1 minus 2, add 5, 1 plus 2a. If we equate that with 0, because we're trying to find the values for which a doesn't have an inverse, we get 0 equals 13a plus 12. Hopefully it's clear how I've found what I've done with this. In order to get the determinant of that 2 by 2 matrix, I've cross-multiplied an AD minus BC. And this gives A is minus 12 over 13. So that's the value of A for which M does not have an inverse. And then we've been told to find the inverse in terms of A, given that M is non-singular. So this is the biggie, inverting the 3 by 3 matrix. So first things first, we're going to form a larger matrix. This is called the matrix of minors, because just as we did earlier in the example we just did, I'm going to find the minor of every element in the matrix. So this is going to be A minus 1, 1, 1. So I just filled in the rest of that there. Hopefully it's clear how I got that matrix of minors. And then we're going to find the determinant of each of those small ones. And we get A plus 1 minus 1, 1 plus 2a, minus 1, 13, 11, minus 4, minus 5a, minus 8, and 3a minus 4. So that's the matrix of minors. And then we need to find the matrix of cofactors. So for this step, this is the step where we look at the corners of the matrix, the corner elements, and the middle element. They all stay the same. And the edge elements, by which I mean these 4, those ones, we're going to make them all negative of what they currently are. That's just going to give us our matrix of cofactors. And then to just combine that with the next step, again for speed, to get the adjoint matrix, it's going to be the transpose of the matrix of cofactors. So once we've made all of these elements negative, we're then going to swap around the rows and columns. So the first column will become the first row, and so on. And if we do that, then we'll get this. So it is a bit of a jump, but feel free to pause the video and think about it for a second to see how I got there, if it's not clear. And then to finish off, we simply have to multiply by the determinant, which we already said was, the determinant was over here, 13a plus 12. So we need to multiply by 1 over the determinant. So I'll just let this equal a. And then it's going to be 1 over 13a plus 12 times the matrix A. That is the inverse matrix of the one they've given us. So it's not too bad. And you won't make a mistake if you just double check very quickly after each step. That's how I like to do it. Just double check after each step. It's only really the matrix of minors step where you're likely to go wrong. The other steps should be fine. Moving on to the next question. A system of 3 equations is defined by the following, where k is a positive constant. Given that there is no unique solution to all 3 equations, show that k equals 2. And then there's some other parts, but we'll just do this first. So to show that k is 2, and this is no unique solution, so the determinant is going to be 0. So forming our matrix, it's going to be K3 minus 1, 3 minus 1, 1, minus 16, minus K, minus K. And since there's no unique solution, the determinant of this will be equal to 0. So we can say that 0 is K times the determinant of this 2 by 2 matrix minus 3 times the determinant of that minor. Add minus 1, so minus 1 times the determinant of this minor. And if you evaluate that, we get 0 equals 2k squared plus 12k minus 32. If you expand it all out, that's what you get. And then you can simply factorize that. You divide through by 2, and you end up getting k plus 8, k minus 2 equals 0. They told us k was a positive constant, so k equals 2. Because it's a positive constant, you should write that as well. So that's the first part of the question done. Might need to erase it. No, it should be. I'll erase it. And then we have to determine whether the 3 equations are consistent using k equals 2. So I'll just rewrite out the equations again using k equals 2. So that gives us 2x plus 3y minus z equals 3. 3x minus y plus z equals minus 2. And minus 16x minus 2y minus 2z equals 2. So we've got these 3 equations, and we need to determine whether or not they're consistent and the geometric configuration of them. So how I always like to tackle these, I'm going to start by eliminating z. You can choose any variable. Z looks like the easiest one here. So we'll eliminate z from the first 2 equations on their own, and then the second 2 equations on their own. And we'll do that first, and then I'll tell you the next step, what I'll do in a second. So to eliminate z from the first 2 equations, I will add the 2 together. And if you do that, I guess I'll save time by just writing out what you get. 5x plus 2y equals 1. Then I want to eliminate z from the second 2 equations. And because I've used the second equation in both of these calculations, that's how we can determine whether they're all consistent or not. So to do that, I will have 2 lots of equation 2, and then we'll add that to equation 3. That will eliminate z, and we'll end up getting minus 10x minus 4y equals minus 2. And the thing about both of these equations, when we've combined them, want to find out whether they're consistent or not. The first one is basically half of the second one, because if we rewrite the second one, we get 5x plus 2y equals 1, just by dividing through by negative 2. So since those 2 equations are the same, that tells us that the initial 3 equations are consistent, which means that there's an infinity of solutions in this case. It would also be consistent if there was only one solution, but since the matrix is non-singular, then, since the matrix is singular, then that being consistent means there's an infinity of solutions. And in this case, the geometric interpretation is going to be a sheaf. When it's consistent, that can imply either that it's a sheaf, and feel free to skip this bit if you're confident with this, It can be a sheaf, or you could have parallel. Sorry, not parallel. You could have all the same plane. And that would be if the initial three equations were all the same. So here, when we've combined the equations by eliminating z from each of them in turn, we've got the same equation. That gives you the sheaf. If all three initial equations are the same, that's when they're all the same plane. And again, that would result in an infinity of solutions. So now we've got a simultaneous equations question where there is a unique solution. These questions tend to be about being able to formulate the equations just as much as being able to solve them using a standard method. So this question is about a college offering 3 courses, construction, design and hospitality. It's all about just picking the relevant information from the question. It really doesn't matter what the question's about. There's a total of 1110 students at the college. So that means that C plus D plus H equals 1110. We're trying to solve these for C, D, and H. And you get 8 marks for this, which is quite decent. And then we're told there were 370 more students enrolled on construction than hospitality. So that tells us that H plus 370 equals C. But to rearrange it and put it into the same form as before, we'll say C plus 0D minus H equals 370. And then we've been told, and they're always, often these questions will include some sort of percentage change. In 2020, the number of students involved on construction increased by 1.25%. So that gives us 1.0125C. Just be careful about the number of zeros and so on here to get the multipliers correct. 2.5% increase in design, and then a 2% reduction, so 0.98, in hospitality. And we've been told that that represents a 0.27 increase overall, so 1.0027 times 1110. If you evaluate that, you get something which is very, very close, but not exactly 1,113. Since it says two significant figures in the question, once you get to this point, you should perhaps use it as that. If you use the exact decimal number, I'll talk about that later. Let's just solve them first. So, putting this into matrix form, we had C plus D plus H, so that's 1, 1, and 1 of each. And then we had C plus 0D minus H, and then we had those long decimal numbers. Timesing that by C, D, H will give us the coefficients, so 1,110, 370, and 1113. Then we use the idea that if you multiply any matrix A by its inverse, we get the identity matrix. So here what we're going to do is, in order to move this matrix over here, in order to move that over to the other side, we're going to multiply both sides by the inverse of that. So that will give us CDH equals the inverse of whatever this matrix is. Let's fill that in. Minus 1 times the answer matrix, if you like. And solving those, which you can just put them in your calculator, and you get that C equals 720, D equals 40, and H equals 350. So if you used instead of 1113, if you use the unrounded value, you'd get answers which were really close to 720, and you'd be expected to just round them. And always worth doing a quick sense check on those answers, that they make sense, and that they look like they satisfy all of the equations, and that is the correct answer. Last question asks us to explain the geometric configuration of the following system of equations. So for this one, so the first thing that we can identify, I suppose, is, well, they're not the same equations because they're not linear multiples of each other. So they're not same equation, and they are not parallel either, because you can't even multiply these by some scalar value to make that side all the same. That won't work either. So they're not parallel. If they were parallel, then you'd be able to make all of these coefficients equal on one side, and then these values would just be different. But that doesn't work in this case, so they're not parallel. You can show that they don't have a consistent set of solutions, and the question which this came from already tells you that there's not one unique solution to this. So we can go straight in and find out whether the equations are consistent or inconsistent. Using the same method as earlier, I'm going to eliminate z from each of those. So we'll have two lots of equation 2, oops, kind of did that the wrong way around, two lots of equation 2 minus one lot of equation 1. If you do that, you'll get minus 9x plus 12y equals minus 2. And then to eliminate z from equations 2 and 3, we can just do 2 minus 3, and that gives us minus 3x plus 4y equals 4. And if we alter this equation to make it closer to the form of this equation by changing the coefficients, we're just multiplying the entire thing by 3, then we get that these two sides are the same, but these are different. And obviously that should be pretty clear that that's not possible, because minus 2 does not in fact equal 12. And so they are inconsistent, and there are no solutions. As I said earlier, I explained why they weren't parallel. And if they're inconsistent, it can only be parallel, or they can form a prism. And so in this case, they form a prism. So the way you always do these, you if you can rule out straight away that the matrix would be non-singular, then you check, are they inconsistent or are they consistent? And that will give you two possibilities for each, which you can rule out by looking at the initial set of equations, whether they might be parallel or the same equation. That's it for today. I hope the video helped with your understanding of matrices. Next video, I'll continue on with the matrix topic by looking at linear transformations. In the meantime, if you found this video useful, I'd really appreciate it, as always, if you could share it with your friends so we can reach as many further mathematicians as possible. Don't forget to comment down below if you have any questions, video suggestions, or feedback on my format or video quality. Thanks for watching, and I'll see you next time. Bye.